Welcome back to the ATA Chapter channel. Today, we're doing a real deep dive, a complete macro-to-micro breakdown of an absolute engineering marvel. We're looking at the revolutionary Airbus A380 hydraulic architecture, which falls right under ATA Chapter 29. You know, the A380 didn't just, scale up existing tech. It literally rewrote the whole rulebook on fluid power. So, in this explainer, we're going to build your understanding from the ground up. We'll start with the core design philosophy, and then work our way right down to the digital brains managing the whole shebang.
Okay, let's dive into this. Here's our roadmap for today. First up, the 5,000 PSI revolution, followed by the two-system architecture. Then we're going to unpack the 3 layers of power generation, map out the distribution to consumers, and finally, look at the digital management systems overseeing everything.
All right, Section 1. The 5,000 PSI revolution, breaking the legacy standard.
So, to really appreciate the A380, we've got to start with its most massive departure from legacy aircraft design. For decades, the commercial aviation standard for hydraulic pressure was, it was basically carved in stone at 3,000 PSI. But the sheer immense scale of the A380, it demanded a radical shift, a massive jump to 5,000 PSI, or about 345 bar. Now, why does this matter? Well, it just comes down to simple physics. Think about it. If you want to move the massive flight control surfaces on the world's largest passenger jet, using that old 3,000 PSI standard, you'd need enormous hydraulic actuators. I mean, incredibly thick piping and just a ridiculous volume of heavy hydraulic fluid. By cranking that system pressure up to 5,000 PSI, engineers could significantly shrink the size and weight of actuators, valves, and piping across the entire aircraft. This high-pressure standard was just a brilliant, elegant solution that kept the A380's weight in check while still delivering unparalleled physical power.
Moving right along to Section 2, two-system architecture, the green and yellow systems.
Right, so now that we understand the crazy pressure running through the veins of the aircraft, let's look at the actual architecture of those veins. Traditionally, large commercial jets rely on a 3-system philosophy, usually green, blue, and yellow. But the A380? It streamlined this into a much cleaner 2-circuit design. Notice the capacities we have here. The green system is just a bit larger, holding roughly 585 liters of fluid, while the yellow system holds about 545 liters. So the crucial point is this, and it's a big one. These 2 high-capacity circuits are entirely, 100% physically isolated. There is absolutely zero fluid transfer between them. None. If a catastrophic leak happens in the green system, the yellow system remains completely untouched and fully pressurized. This strict isolation is literally the bedrock of the aircraft's safety profile.
Okay, Section 3, Power Generation Layers, Building Redundancy.
Moving from architecture to muscle, we really need to categorize how this incredible 5,000 PSI pressure is actually created. In a 2-system aircraft, redundancy isn't just important, it's absolutely everything. To index this clearly in your mind, try thinking of power generation as a matrix of 3 distinct layers. First, we have the main generation layer, which is driven mechanically by the engines. Second, there's the auxiliary generation layer, driven by 4 electric motor pumps. And third, we have a super innovative local backup layer that operates totally independently of the main hydraulic lines. Let's break these down visually.
And this brilliantly illustrates the main generation layer. Notice the 4 engines there, and see how each engine is equipped with 2 engine-driven pumps, or EDPs. So that gives us a total of 8 EDPs during normal operation. Engines 1 and 2 supply the green system, while engines 3 and 4 supply the yellow system. Now look really closely at the routing from the reservoir to the engines. You'll spot a fire shutoff valve, an FSOV, positioned right before the fluid splits to the 2 EDPs on each engine. Why? Well, in the event of an engine fire, closing this single valve instantly cuts off flammable hydraulic fluid to that specific engine, all while the other engines just keep on pumping normally. Pretty clever, right?
But what happens if you lose those main pumps? Or, worst case scenario, you suffer a total loss of fluid in the green or yellow lines? Well, this is exactly where localized backup generation comes in to save the day. Out on the flight controls, we have EHAs and EBHAs, that's electrohydrostatic and electrical backup hydraulic actuators. And then down in the braking and steering systems, we've got LEHGS, local electrohydraulic generation systems. Basically, these components use the aircraft's electrical power network to run self-contained, localized hydraulic pumps. Because think about it, electrical wires don't leak fluid. Even if a main hydraulic pipe is completely severed, the aircraft's electrical system can just step right in, generate local hydraulic pressure right there at the actuator, and make absolutely sure the pilots maintain critical flight controls and braking. It's a real game changer.
Which brings us to Section 4, Distribution and Consumers, where the power goes.
So now that we've generated all this power, where exactly does it go? This matrix clearly divides up the system consumers for us. Think of the green system as handling your forward and outer elements. It drives the nose landing gear, or NLG, the wing landing gears, the WLG, and operates the cargo doors. The yellow system, on the other hand, takes the heavy center loads. It powers the body landing gears, the BLG, and the body wheel steering, the BWS. But hey, look at the bottom row. For the primary flight controls, like the ailerons, elevators, and rudder, both the green and yellow systems actually share the critical loads. This guarantees that no matter which system is compromised, aerodynamic control of the aircraft is always maintained. No single point of failure there.
Finally, Section 5, Digital Management, the HSHUs.
Now, an architecture this massive and complex, it just can't be managed by traditional mechanical relays alone. It needs digital commanders. Down in the avionics bay, you have two digital brains, the green HSMU, designated 1JG, and the yellow HSMU, designated 1JY. Now, what's really interesting about this is seeing how these units act as the critical bridge. They sit right between the 5,000 psi pumps out on the pylons and the visual indications the pilots see directly on the cockpit system display.
These HSMUs are just relentless. I mean, every fraction of a second, they're monitoring fluid pressure to make sure the pumps are doing their job. They track fluid temperature to stop the system from overheating during high demand. They're constantly monitoring the reservoir quantity, always watching out for leaks. But beyond just monitoring, they actively control the logic for those auxiliary and local electrohydraulic pumps we discussed a minute ago. They literally decide when to automatically bring those electrical backups online. And if anything falls out of parameter, the HSMU triggers precise local warnings on the control and display system to alert the flight crew immediately.
So what does this all mean? Well, it really begs the question. When you consider a highly pressurized 5,000 psi network pushing over 1,000 liters of fluid across an airframe the size of the A380, just how much engineering precision does it take to safely manage this lifeblood? The transition from 3 systems to 2, that layered electrical redundancy, and the incredible digital oversight of the HSMUs, it all represents an absolute masterclass in modern aviation safety and efficiency.
Please like, share, and subscribe to ATA Chapter for more professional technical training. See you in Part 2, where we dive into engine-driven pumps.